Morning, everyone. My name is Liam, and I'm a PhD student at the University of Strathclyde in Scotland. I'm funded by the EPSRC. I'm part of the Wind and Marine Energy Centre for Doctoral Training, and this project was originally part of a collaborative project with Vattenfall. So very short-term wind power forecasting using regime switching for power amps. I should clarify that very short-term in this context is between 10 and 20 minutes ahead. So it's a much shorter time horizon than Jethro was talking about. So very quickly, I'm going to talk about wind energy in Europe very briefly, the value of very short-term forecasts in that context, what power amps are and how they affect power system operation, and some results from a really interesting case study at Horns Rev. So wind in Europe, approaching 200 gigawatts of installed capacity. I think we might be there right now. The trend, especially offshore, is to construct large wind farms. People talk about wind penetration, which is the total electricity demand, a percentage of the total electricity demand which is met by wind generation. Here in Denmark, it's in the 40%. In GB, where I'm from, it's about 20%. Wind energy is stochastic, which means you can't know what your production is going to be in the future. You've got to make a forecast. Forecast has errors, and the errors add to the uncertainty of the power levels in the network. And if you're a system operator, it's your responsibility to balance the power flows in the network. And you do this by deploying balancing services. So these are grid-connected infrastructure that can change either their input or output of power to the network. So the most big generators or heavy industry or grid-connected batteries for storage. And the amount of uncertainty that you have in your power levels is determining how much balancing services you need to contract. So as we increase wind penetration, the amount of balancing services increases. There's a study from the EIA Task 25 that showed that the cost of balancing a system goes up with the wind penetration. So in order to recoup some of the costs, the network operator requires stochastic generators to make very short-term forecasts. Then they issue fines to the stochastic generators based on forecast error, because that's directly correlated to how much balancing services you need. So the incentive from a wind power producer's perspective to decrease their error in very short-term forecasts is to basically just reduce the amount of fines that they're paying. This is 1 day's worth of half-an-hour settlement periods and the cost of balancing the network to the system operator. And the forecast horizons that are required are the same as the balancing services contract length, so that half an hour or 15 minutes, depending on which country you're in. So what is a very short-term wind power forecast? Well, wind power time series tend to be quite persistent, so often a persistent forecast is used, especially in 5, 10, 15, half an hour timescales. If you're going to beat a persistence forecast at that timescale, you'd probably use an autoregressive model, which is a simpler version of what Jethro was talking about, where basically your power is a linear function of power history. But all these models that are used on this timescale are statistical, and what I mean by that is the only information they use to make a forecast is the time series itself, so the lagged powers. The reason for that is that there's no forecast skill in using numerical weather predictions and a power curve at such short timescales, or so people think. So I'm going to look at a case study now. Horns Rev 1 is a big offshore wind farm, 160 megawatt capacity. It's typical of the kind of capacity that's getting installed now. It's also a very rampy wind farm, which means that power fluctuates quite a lot. Every wind farm is exposed to power amps in some way, and they very much affect the quality of the autoregressive forecast. The reason for that is that if large power ramps basically mean that when you're doing linear regression, you've got a very noisy signal. And linear regression tries to minimize the squared error, so if you have very large deviations, it affects the fit of the linear model adversely. So as an example, in this 12-hour period in Horns Rev, there was 8 events where the ramp rate exceeded 5 megawatts per minute, which is extremely fast, represents a third of the rated capacity of the wind farm over 10 minutes, which is astonishing. The causes for this, the main cause is a change in axial flow with the wind speed through the rotor disk, and that's caused by, we don't necessarily know, but have some guesses that it's caused by weather phenomena like extreme thunderstorms or other kinds of convection or cold fronts passing over the wind farm and rapidly changing the wind direction, or unknown. I mean, I heard at this conference that Horns Rev has warm water upwellings which cause power ramps, so the more you know. If our hypothesis is correct that the power ramps are to do with actual structures in the atmosphere that we can measure, it's a perfect time to apply a regime switching model. As Jethro already said, it's where you're trying to predict a variable and you suspect that there's two or more distinct behaviors that are driving the behavior of that variable. And so in this context, what you would do is you try and separate all your training data into two separate groups which represent the two behaviors, and train two different models, and then apply the different model in the regime that you think you're in at that time. The handy flowchart there. And so you need an extra variable to act as a classifier. So you might set a boundary condition, a boundary for this, or a threshold for this variable. When it's above that threshold, you're in regime 1. When it's below, you're in regime 2. But I'll try and illustrate. So this is about half a week's worth of power time series from Horns Rev. As you can see, quite variable output. I'm going to overlay on top of that the boundary layer height forecast from ICEM, which the power traders who make the forecast already have access to. And if we say we apply a threshold of boundary layer height, say in this instance it was 710 meters, so that's the forecast boundary layer height for that time step. Then in every time step when the boundary layer height forecast exceeds that, we can now say that data is in regime 1, highlighted here in red. So you remove that data, put it together with all the other data that's in the same regime, and train a linear model to that, and then take all the other data and train another model to that. And then you know ahead of time, because it's a forecast that you actually have access to, which model you're going to be using. So in terms of the experiment, I had to compare it to the baseline, and the baseline used at Vattenfall at the time was not a regressive model. I had access to 10-minute SCADA data, so I was forecasting one time step ahead. In Vattenfall, they have to do 5, 10, and 15-minute forecasts every 5 minutes. Auto-regressive model of order 3, that means it used 10, 20, and 30-minute power lags, which was the most efficient one for this case. And use mean absolute error because that corresponds to the actual fines that you're going to pay. The regime switching model is the same order model, exactly the same, just trained on segregated data sets. I'll talk about this graph later on. So I basically took as many data variable sets as I could from ICEM, which I thought had to do with things that would predict structures in the atmosphere, like convection, or so sea surface heat flux, convective available potential energy, things like that, and did a grid search, choosing random thresholds in those, well, not random, but thresholds in those data sets, and seeing if you split the data, the power series data, by that threshold, do you get a performance increase? That's a 2-regime model. And the results, some of the results are here. I also took some things extra from the SCADA data, like the lag standard deviation, and that was the best predictor, as you can see. And the best predictor from the numeric weather prediction models was the boundary layer height in red there. Interestingly, the biggest overall improvement was a very low value of standard deviation, lag standard deviation. And that's because if the standard deviation was very low in the past, 10 minutes ago, that means you're probably at a persistent regime. So you're probably at 0 or rated or some sort of curtailment. And there's a lot of curtailment happens at Horns Rev because it's got a very active wind farm controller, and it's also being curtailed all the time by the system operator. So then I increased the model to have 2 regime classifiers and a 4-regime model. And also when the standard deviation, a low standard deviation was used, 2 of the models got turned into persistence to make a 3-regime model, and that boosted performance. So as you can see, with the 2 variables being the standard deviation at 10 minutes and also at 20 minutes history, we were able to get a 3.82% mean absolute error improvement over the baseline autoregressive model, which is, I think, very impressive. I'd also like to draw your attention to the bar at the far right-hand side, where boundary layer height and predicted wind speed, so they're both numerical weather prediction variables, had a 1% improvement. The reason that might be more useful is because you know, like 12 hours ahead, or you know from forecast issue time which regime you're going to be using at which time, which model. There was some, I don't know what time it was.
You still have time.
Okay. How much time?
4 more minutes.
Cool. So the results are the result of k-fold cross-validation training. I also had an extra data set which I didn't have any information that I could use to clean it with, and I applied some of the models to unclean data. And it was quite interesting because the standard deviation classifier was very good at dealing with data that was unclean, because, as I said, it's really good at identifying those persistent regimes. And some of the worst sort of offenders in the unclean data set is when you have curtailment, especially curtailment that's not registered in the balancing mechanism, so you don't have any information about it. And that'd be from the wind farm controller. So standard deviation as a classifier performed basically exactly the same, actually a bit better in a whole year's worth of forecast trial. But the improvement of the numerical weather prediction models did not work when the data was unclean. And I think that's because you wipe out the improvement that you get from splitting into regimes by having lots of unclean data in there. So if I had perfect curtailment knowledge, which you might do in an operational context, then the numerical weather prediction classifier should work well still. I don't want to say too much about this graph because it's such a small picture you can end up making things up. But I would like to say a few things about, firstly on the graph on the right. As Jeffro said, a lot of the numerical weather prediction variables had very large seasonality, and I sampled the K-fold, the folds for K-fold across the months basically. So a lot of the improvement could be to do with just seasonality in which model is actually better in which season. Also, I'd like to say the standard deviation, you can clearly see that in the forecast in red is closer to the actual power value in black. And that's basically because it's identified a persistent regime, so there's no sort of steady state error when you're looking at in that regime. Also, the red forecast, especially in down ramps, if you're in a down ramp, it means that the 20-minute or 30-minute power lag is much larger than normal compared to the 10-minute power lag. So it has the coefficients that correspond to those 10, 20, and 30-minute time steps have a much larger effect, which can mean that you miss the bottom of the power ramp, but standard deviation helps. Also, if you're trying to clean data, you can use standard deviation to identify where you might be curtailed if you don't have the information. So quickly, conclusions. Basically, a very commonly used model, autoregressive. People use this in trading rooms and the power dispatch centers all the time. Can be improved with a really simple regime switching model. There's also extra forecast skill in numerical weather prediction models that you already have access to. Regime switching benefits are twofold because you're using the most appropriate model, but the model is also trained on less noisy data, so it's actually a more efficient model, or better performing model anyway. And the standard deviation is a good classifier even in noisy data sets. Further work, I'd love to check every single regime classifier possible, and also do some feature engineering with the classifiers to sort of maybe have a storm or a weather front feature. And also do the same thing with high frequency, so I can check that the results are the same with 5, 10, and 15-minute air forecasts. Thank you very much for listening, and I'll take some questions.